This is the final presentation for the analysis and redesign of a coffee bean grinder. The purpose of the coffee grinder is to grind whole coffee beans to produce coffee grounds. We anticipate a yearly volume of 200,000 parts. Here is the bomb and exploded view for the coffee grinder.
Primary and secondary customers. The primary customers are coffee enthusiasts who care about what goes in their coffee and how it is prepared. The secondary customers are the coffee drinkers, looking to reap the benefits of fresher tasting coffee.
The fast diagram shows that the main functions are to contain beans, add rotation, drop grounds, and contain the grounds.
We analyze the product to generate different possible assembly sequences. We select the first proposal based on the advantages identified.
This is our bill of material and rough cost estimates. This is the quad chart highlighting items that are recommended to be redesigned. Here is the functional component mapping matrix for the coffee grinder. Here are the functional differentiation table and the component commonality table.
Two modules were generated based on the functional differences, especially in the energy source. The rest of the components are part of the platform. The grinder support provides the common interfaces to both modules. Meanwhile, the lateral gear can be attached to either version. The final assembly sequence of the platform, including the different modules, were optimized to improve the efficiency along the process. As a consequence, the product family assembly diagram is simpler and is focused on the application of the delay differentiation concept.
Design for manual assembly analysis was performed on the coffee grinder. The results show that the total manual assembly time is 237.9 seconds, resulting in an assembly efficiency of 16.4%. For our platform component, the bean collector was chosen to be redesigned. Per our quad chart, it has high functional importance and high manufacturing costs, calling for a redesign. In addition, it also has high assembly time due to being difficult to align to the base and being secured with 4 screws. The module components were chosen due to their long assembly time. The gears and cranks both need to be carefully aligned to their respective shafts so that their fastener holes align with the fastener holes in the shaft. Together, the platform and module account for 46.2% of the manual assembly time. Being able to improve both areas could lead to large reductions in the total assembly time. Using the DfA1 and DfA2 concepts of reducing part counts and reducing fasteners, the components of the bean collector and base were combined into one unit. Combining into a single piece eliminates the need for any alignment between the bean collector and base during assembly, and also eliminated the 4 fasteners. DfA1 and DfA2 of reducing components and fasteners were used to improve the platform components. The crank subassembly was moved to directly attach to the main shaft. This eliminated the lateral shaft and both gears. By eliminating the gears, this also eliminated the set screws to secure them and the careful alignment required during the assembly process. With the design changes to the coffee grinder, the manual assembly time was reduced by 85.6 seconds. This part consolidation and resulting assembly time reduction improved the assembly efficiency from 16.4% to 19.7%. These improvements were made without any functional impacts to the coffee grinder.
For our design for automated assembly analysis, we selected the container subassembly, which is composed of the outer grinder cuff, fixed cover, slider cover, shoulder bolt pivot pin, and slider cover pin. Our quad chart identified the fixed cover as a component well suited for redesign because it has a high manufacturing cost. This component has no locating features, increasing the difficulty to align and secure the component properly. Also, this subassembly contains several small components that work well for an automated assembly process. We performed the analysis of the subassembly to calculate the total handling and insertion cost, which I will show in the next slide. From this analysis, we identified some opportunities for design optimization that will decrease handling and insertion costs while conforming to design guidelines. The first change we made aligns with the design guideline DfA10, add features for easy insertion. Chamfers were added to the inner cuff, slider cover pin, and slider cover for easier insertion. The second change we made aligns with the design guideline DfA11, provide locating features. For this, locating features were added to the fixed cover and base for easier alignment during assembly. Here we are showing our automated assembly analysis and total assembly cost results. The initial analysis, the top table, shows our original assembly cost was $8.21 per part. After implementing the design changes per the guidelines I covered, the redesigned part assembly costs are now $7.20 per part. This is about a $1 reduction in total assembly cost per part. The proposed changes are minor and should have minimal impact to the part costs and no functional impact to the coffee grinder.
The two parts chosen for process selection were the redesigned base and the crank from the design for manual assembly. The base process was chosen to be injection molding based on the attributes determined. The crank was chosen to be machining based on its attributes. Below are the key dimensions for the redesigned base and the crank. The dimensions for the base are on the left and the dimensions for the crank are on the right. The ones circled in red are the critical dimensions. The critical dimension of the base is that the diameter of this feature is important for the outer grinder cuff to fit properly. The critical dimension for the crank is that the diameter of the hole is important for the main shaft to fit properly.
The first parts that were designed for manufacturing are the base and bean container, which were injection molded together via a single cavity. There were 4 DfM changes made. The first is that per DfM Pro's 1 recommendation, a 1 mm radius was added at the intersection of the base and bean container to prevent sharp corners. The second is that the maximum wall thickness was reduced from 10 to 5 mm to greatly reduce cooling time. The third was that the core lifter was eliminated from the tooling by opening up the front face of the base and enlarging the collection box, thereby reducing the overall mold cost. Finally, a draft was added to all surfaces. In terms of the cost of the manufacturing the part, you will see a 51.4% overall cost reduction from before the DfM process and then after redesign, which is a significant reduction. And there are 2 main design drivers for this cost reduction. One is the reduction of maximum wall thickness from 10 to 5 millimeters, and the second is changing the design to eliminate the core lifter. And you will see the cost and timing impacts shown in that chart for those changes. And finally, the elimination of the core lifter not only significantly reduces cost and time, but it also allows the collection box to hold more coffee grinds, thereby increasing the product functionality. The second part that was designed for manufacturing is the crank, and this was machined via a CNC machining center. There were 3 DfM changes made. The first is that per DfM Pro's 2 recommendations, the top and bottom surface long fillets were eliminated from the part, thereby avoiding the need to flip the part and reducing setup time significantly, and also significantly reducing overall machining time. Secondly, the set screw hole was eliminated from the part on one end and replaced with a D slot that has the same function. This avoids drilling into a non-flat surface and also avoids a non-standard drill size. Finally, overall part curvature was eliminated, making a straight part, enabling use of a standard bar stock and minimizing material waste. In terms of costs, it was reduced overall by 54.9% from $4.67 to $2.11, and the primary driver of this was removal of the long fillets on the top and bottom sides of the part. This primarily impacted non-productive time, so setup time of flipping the part and tooling changes, as well as machining time that is required to machine those long fillets. The website hubs was used to quote the cost of CNC machining the crank before and after redesign. Using a PowerFit to extrapolate the value up to x equals 200,000, quotes of 64 cents and 31 cents respectively were given for before and after redesign. However, because these values don't correlate super well to the data, taking just the last few data points which fit much better to the power line yields hubs quotes of $4.60 and $2.33, which are closer to our analytically calculated values.
The inner grinder is expected to dull over time as a customer grinds beans. An inner grinder replacement service will be offered. A resharpened inner grinder will be sent to the customer and the customer will send back their original inner grinder. The original inner grinder will be resharpened and sent to another customer. This prevents customers from having to purchase a new complete grinder, allows the continued dependability of the coffee grinder, and reduces environmental waste.
Here we show an image of the final coffee grinder. This redesign has a reduction in assembly time and automatic assembly and manufacturing costs. However, one potential issue we've identified is ergonomic difficulties may arise from attaching the crank arm to the top of the coffee grinder. Also, the machining process for the crank may leave sharp edges. If we were to start over, our approach would be to start with a new design concept that would allow for a manufacturing-focused design while meeting customer requirements. We also suggest benchmarking top-selling competitors to understand competitor wins from component manufacturing and ease of assembly.
Thank you.